Hello, my name is Sam Jabley, and you're going to be watching my video lab report for Lab 1 Constant Velocity. For the introduction, in this lab, the position versus time graph of a round object that is rolled at constant velocity will be measured, and that experimental data will be plotted and will also be compared to a theoretical model that will be created using GlowScript code. The observed positions of the object in the experiment will be compared with theoretical positions the object should occupy at any given time. And this comparison between the computational and experimental models is going to help illustrate the concept of Newton's second law of motion. And that is the purpose of this lab. So, some small details about the experiment. The object is a round orange bouncy ball, and this will also serve as a system in the experiment. The final position is the white barrier that the ball hits at the end of its roll. The experimental model will be made using Tracker, and the computational model was made using GlowScript, and the surroundings is everything else. So, some background on Newton's second law of motion. According to the second law, the net external force upon an object made in a straight line is equal to the change in momentum of that object divided by the change in time. And taking the formula for net force and subbing in the formula for momentum and doing some rearranging, you can derive the velocity update formula, which proves that an object with constant velocity, meaning no net force, will have the same final velocity as initial velocity. So, for my experimental model, I rolled my orange bouncy ball across the desk until it hit the white barrier, and I used point mass tracking in each frame to get the data points seen in this graph. The graph looks largely linear, but you'll see that it undershoots compared to the computational model. Some data from the tracker. I got the total time to be 0.6 seconds and the delta t to be 0.4 seconds since it technically started in the first frame at 0.2 seconds. I got the initial position and the final position from the data in the graph, and I was able to find the average velocity vector by taking the change in position over the change in time, which can be seen right here. Now, some coding for the computational model. In lines 36 and 37, I changed the information in the vectors to represent the position initial vector that I calculated from before and the average velocity vector that I calculated from before. I also changed delta t to be 1 over 30 since the frame rate of my video was 30 frames per second. In addition, I set fnet vector equal to 0 because the net force is supposed to be 0 when an object is in constant velocity. I also changed lines 59 and 61. In lines 59, I made it into the velocity update formula, and I changed line 61 into the position update formula. So here's the results of the computational model. As you can see, the line looks very similar to the experimental model, but you're going to see that when they're compared, the computational model far overshoots the experimental model. So some possible errors as to why this occurs. Tracking. It was difficult to place the position trackers in the exact center of the rolling ball in each frame, so the data in the experimental model could be slightly altered as a result of this. The main reason, however, is likely due to outside forces. The reason the experimental graph sees lower position values is because of outside forces such as friction and air resistance acting on the rolling ball. These forces cause a net force to be exerted, meaning that the ball does not truly have constant velocity in the experiment. It would be very hard to make the ball actually have constant velocity in real life, because we aren't in space. Rounding. Rounding errors could also accumulate and affect some data entries, although it's probably minor errors. So, some discussion questions. What if the positive x-axis became the negative x-axis and vice versa? If this was the case, nothing would really change about the experiment except for the slope of the graph. The slope would become negative since the ball would be rolling from x equals 0 towards a negative number instead of towards a positive number. Is it possible to say how many forces were added together to give 0 net force in the case observed? When comparing the two models, the computational model overestimating the position shows that there are other forces like friction and air resistance at play in the experiment that are causing the net force to be non-zero, which was explained during the errors. Thank you very much for watching. I hope you learned a few things from this lab, and I hope you have a good day.